going to solve problem related to the system of linear equation. Our first problem is solved by using all three known methods if applicable for this system. So here we have all three known methods. We are going to discuss three methods, which is the inverse method and Cramer's rule and then Gauss elimination method. So here is if applicable means if the determinant is equal 0, then inverse method cannot be applied. In that case, we will try to solve it by Cramer's rule and Gauss elimination method. So let's start with the inverse method. So first we'll write this system in the matrix form Ax equal B. In this case, A is this matrix from the coefficient. We will get it 1, minus 1, 1, and then 2, 3, minus 1, and this is 1, 1, minus 1. And then we will have the matrix X, the variables X, Y, and Z. Then we will have the matrix B, which is the non-homogeneous part, the constant 2, 5, and 6. Now, let's start with the inverse method. So for that we calculate the determinant of A. So determinant of A is given by this, and the answer is 4, which is not equal to. So therefore, the coefficient matrix A is invertible. So we will calculate the inverse of A. So since determinant of A is not equal to 0, so we can solve this equations by all three methods. And if determinant is not equal to 0, the system will have always unique solution. So we will try to find that unique solution by three methods. First, we will calculate the inverse of A. For that, we will calculate the adjoint of A. So adjoint of A is the cofactor matrix for all entries. So it will be 3 minus 1, 1 minus 1. So it will be minus 2. And same way we calculate it for all entries cofactor. And then we'll take the transpose of this matrix and we'll get the adjoint of A. And we know that A inverse is equal adjoint of A divided by A determinant of A. Determinant of A. So that will give us this matrix. After dividing by minus 4, this will get this matrix. So next we'll have here the A X is equal X, Y, Z. This variable will be A inverse B from this system. So therefore we got A inverse B. So A inverse is calculated here and we will multiply with B. So it will be A inverse B is like this. Multiply this. After multiplications we will get the solution is 1, 2, and 3. So therefore we have X is equal 1, Y is equal 2, and Z is equal 2. So this is the solution of this system by inverse method. Let's move to the next part of this. So we'll have now time system and the matrix form. Then we calculate the determinant, which is equal minus 4 as previous method. So then we'll have here this system have solved by all three methods, and then we'll have the unique solution. So we'll calculate D1. D1 is we'll have here that 250, the first column is replaced by this vector B. So therefore, we'll get it here. The determinant, we calculate it, and then the determinant is equal minus 4. So D1 is minus 4. Then we'll have D2. So D2 is equal this value. So now, how we calculate D2? We'll take this determinant A and change the column 2 by the vector B. And then you will get D2, and then D3 is same way on the determinant A, change the column P by the vector D. Then after calculation, we get it, this one is equal minus 12. Then by the Cramer's rule, the solution is given as here, x is equal D1 over x is equal D1, determinant D1 over the determinant of A. So which is equal minus 4 over minus 4 is equal 1. Then we'll have y is equal, same way, determinant D2 over A minus 8 minus 4 is equal to, and then g is equal determinant D3 over determinant of A, which is minus 12 over minus 4 is equal to. So therefore, the solution is 1, 2, 3, as in the previous method. Now, next is come to the third method, and in this method, we will have same way write the matrix form of the given system. Then, since we are doing for the Gauss elimination method, so it is not required to have the determinant. So we will take the augmented matrix. The augmented matrix is given by this form. So here we take the coefficient matrix A and the constant B in this. Now we will do the elementary row operation, and for the Gauss elimination method, first we have to check it. The first column need to be 0. So we need to make this part 0. So now we'll do how we'll do it. So that's we'll discuss now. So for that we will do this row operation. R2 is R2 minus 2 R1. So to make this 2 is 0. And then we will do another operations R3 minus R1 on R3. So this will make this entry is 0. So let's add that. This will do it, this operation. So after the operation R2 minus 2 R1, so you see that this is 0, this is 3 minus plus 2, so it will be 5, and this is minus 1 and minus 2, this is minus 3, this is 5 minus 4, which is 1. So we continue with this, and then we'll have in this form. So our target is fulfilled, that this is equal 0. Now we need to make this one 0. So to make this one 0, we do little bit a different calculation. We can make this is equal, is divided by 5, then it will become 1, and then you can calculate it to make it 0, or we can also take any other method. So this transformation or these operations are not unique. You can always have choice for you to do your own operations. Main target is that this will be 0 and then this will be 0. So diagonal entries, below the diagonal entries, the entries will become 0, and you should have a upper triangular matrix of the coefficient part, not the whole augmented matrix. Only the coefficient matrix parts you need to convert it to the upper triangular matrix. So now in this case, what operations we can do? What we did here, R3 is R3 over 2, because this 2 is common for everyone. So therefore, we will not have any fraction. So try to avoid to do such operation where the fraction will appear. So that will make calculation more complicated. So therefore, we divided R3 as R3 over 2, and then we will have here in this form. Now we exchange this R2 with R3, and then we'll have this. So now since this entry is 1, so it is very easy to make this pi 0. So this operation we did it because to avoid to have any fraction in the calculation. Now we make it R3 minus 5 R2. So this will gives us in this 1, 1, 2 sun rectangular matrix. So you can do now from directly to get the solution, or you can do another steps divided 2 and 6. So this R3 over R3 over 2. So this will gives you this form. So now from this we can have the solution. So this is the most row reduction form, and then we will go back for the solution. So take this one. This row can be equivalent to z is equal to 3. So you will start with always the third row, and then since this entries are 0, so you will get the directly value of the third variable. So this will give you g is equal to. Then move to the second row, and then you will have two variables. One is y minus g. So this is equal minus 1. So now the value of g is already known. You can calculate the value of y. Now the first row can be written as x minus y plus g is equal to. The next step is to the solve using back substitution. So back substitution is the first one is known, then we will use that with the second one, and then first and second use the third one. So g is equal to d is known, and then from this second equation we will get y equal minus 1 plus g. So that will give you minus 1 plus 3 is equal to. And then from the last equation we will have x is equal to plus y minus z. So now y and z already known. So therefore you will get it here. 2 plus 2 minus 3, which is equal to 1. So therefore you get the solution is x equal 1, y equal 2, g is equal to 3. So that's the methods will give. All three methods gives you same equation, same solution. And let's complete the first question.